Okay. Hi, everyone. Thanks for coming. We're going to have today's seminar, we're going to have Gabor Sarosi from CERN give us a talk on comments on the volume of the black hole interior in 2D gravity. Thanks so much, and please.
Well, thanks, Nima, and thank you very much for this invitation. So I'm going to tell you about some work that I've done almost a year ago with Luca Iliescu and Mark Mezei. And also I will tell you about work in progress. That's a straight follow-up of this that we're working on with Luca, Mark, and Alexei Milekin. Yeah, so please also just feel free to interrupt me if you have any questions. Okay, so this will be the plan for today. I will start by a very short motivation of the problem that we're trying to solve in the long run. Then I will describe you our calculations and definitions of the volume of the interior of a black hole, a two-sided black hole in JT gravity, which is a 2D theory of gravity. And then the third part, which is the very much work in progress, will be about the microscopic interpretation of what we find in JT gravity. Okay, so let's start with the motivation. So what we want to understand is the growth of the size of the black hole interior. So here's a black hole in ADS. It has two sides, and the interior is kind of expanding. In fact, it kind of behaves like a cosmological space-time. If you just look at this interior region, it sort of expands. There's some maximal slice, and then it actually shrinks and crunches at the singularity. So what we want to understand is like where is this creation of space comes from. Okay, so one very interesting gauge invariant probe that captures this is the volume of a maximal Cauchy slice. So when we're in ADS, we can kind of fix a time at the boundaries. Let's call that T, and can look for a maximal slice that goes through the bulk, and you can ask about how the volume of this slice changes. And it turns out very universally that it, for large times, it grows linearly with time. The coefficient is basically the mass of the black hole. Okay, so we want to understand this growth. So in the ADS-CFT duality, the question is what's the microscopic origin of this creation of space here? Okay, so we want to address this question in ADS-CFT because there we have a handle on the microscopic dual. In fact, we understand the state itself. So if you look at this two-sided black hole, it's dual to this famous thermophile double state, an entangled state of the left and the right. And if I write it this way, it's a state that is living on this time reflection symmetric slice. So we can do a time evolution on both sides upwards. So this is not an isometry of this geometry, and correspondingly, this is not an eigenstate under this evolution. So you get a new non-trivial state. So now we are looking for some property of this state that captures the size of this Cauchy slice. And one traditional kind of argument why this is a special quantity or must be some special quantity is that this is some kind of thermal state, basically, and then you perturb it in some way. And conventional probes of the state, basically, you expect them to thermalize in some time scale that is set by the energy of this state or some temperature that is built into this state. So the question is, what is it that's capable of growing way past this kind of time scale? What grows long after thermalization? Okay, so there's a candidate kind of quantity or family of quantities, let's say, that is proposed by Susskind and collaborators, which is called quantum complexity of a quantum state. And roughly you can think about this as the following. You're given some reference state, so let's imagine it's k qubits, all in the zero state, and then you're also given a target state, and your task is to get from the reference state to the target state with the minimal resources, and the resources that are available are 2-qubit gates, let's say here. So these particular details are not important, but the important point is that the set of resources is restricted in some way. So now you can build these quantum circuits that go from the reference state to the target state, and you can ask what is the least amount of gates that I need to use to be able to perform this task. And then the size of this minimal quantum circuit that you find, you could call it the complexity of this target state. Okay, so this is a very ambiguous definition I gave you. Already for qubits, it depends on a lot of things, how you choose this reference state, what are you allowed to do here, what kind of 2-qubit gates can you put multiple qubit gates, and so on. So this is a rather ambiguous definition, but actually how we measure the size of the interior is also a rather ambiguous thing. So we can do it by the volume, or we can have other proposals, other gauge invariant quantities, like there's an infinite number of them that will equally well measure the size. Okay, so what's the important thing is basically how these kind of complexity quantities scale, let's say, at long times. So what are the generic features that are common to all of them? Yes, so let's focus on universal behavior.
Sorry, Gabor?
Yeah?
Do you want to say a few words about if it's quick, like if it's not detour, changing the direction we're talking, what are these infinite number of gauge invariant quantities that you're thinking of involved?
Yeah, so basically one thing that we have shown in this paper is that you can kind of pick some function, like you're doing an action and you add higher derivative terms to an action. You can add higher derivative terms to data on a surface, on a Cauchy slice as well. And then you can extremize this whole thing. And then there are some couplings there that come with the higher derivative terms. But you can just look at this as an observable in Einstein gravity, so without actually changing the action. And if you do this, it's very generic, that what you get also displays this kind of behavior, that it scans the size of the interior in the sense that it grows linearly with time at late times, and its growth is proportional to the mass. But this is just like observables that are restricted to a Cauchy slice, but you could also cook up observables that are scanning a space-time region. So for instance, there is the complexity equals action proposal, where you consider the action of kind of a causal diamond called the Villers-de-Witt patch ending on a given Cauchy slice. So that also displays this kind of behavior. And then you can also deform these kind of observables as well, and still not spoil this.
So can I ask for like a maybe generic question? So when you evolve the state and nothing's gonna happen, I guess, as you say, the complexity will increase, but in the other situation, you will crash against the singularity. Is there any idea of what that would be in terms of the state?
So very good question. Yeah, so there aren't any good ideas, but one thing to note is that if you really just consider this observable, where the way you make it gauge invariant is that you fix where it lands on the boundary, then you cannot move past the maximal slice. So there's a slice here that's sort of maximal, and beyond that it starts to crunch, but that maximal slice ends here at the tips, and that's what this thing hugs as you move forward. So this probe is not sensitive to that region, it can only access the expansion.
So you think there is another quantity that will determine that there is a singularity, so another quantity in the...
Yeah, you need to look at some other quantity, but we are not sure what would that quantity be.
Thank you.
Sure. Thank you for the question. Okay, so I was talking here about quantum complexity as like a potential kind of dual to the size of the interior. So yeah, so let's kind of summarize what's the expectation from complexity, like what's the kind of universal behavior that people expect is that we have a regime where you have this linear growth that we have also seen for the volume. So this is a long regime where S is the entropy. And then after a while, even though like this quantity is not thermalizing for a very long time, after a while you just run out of states in the Hilbert space. So you're basically getting to some generic, very typical state, like a hard random state on the given, let's say, energy shell that you're living at. And at that point, you would expect complexity to not grow anymore. So the expectation is that you have this linear growth for a very, very long time, exponentially long time in the entropy of the system, and then you have a plateau, complexity plateau. And then at even later times, double exponential times, you could even have recurrences, but I will not be talking about those. Okay. So this is what semi-classical gravity is supposed to capture, that this wormhole or this interior growing linearly is this linearly growing regime. But semi-classical gravity doesn't really see this saturation. And then the focus of today's talk is to try to nevertheless see this in gravity. Okay, so that's what I'm going to try to talk about. Yes.
Question. This might be a little bit mathematically too mathematical for this discussion, but like, so it is true that as you said, well, probably I'm assuming that you're going to consider the case of SYK, where you have finite dimensional Hilbert spaces. So then there is actually these behaviors that you're discussing, right? Recurrences and such. But if I'm thinking of the TFD as two CFDs living on infinite volume, strictly speaking, these are infinite dimensional Hilbert spaces, right? So this argument is a little bit hand-wavy. Do we expect a version of this argument to go through more rigorously in those cases, or?
Yeah, basically, yes. So if you, for the thermophile double, there are some exponentially small tails that you might need to worry about, but you could kind of truncate it into like an energy window.
But I mean, the behaviors such as like recurrences and those things are such long time scales for which these truncations, might not be good approximations. Or anyway.
Yeah, so for the recurrences, there might be some difference in that case, but for the saturation, this will probably not matter.
I see.
Just because yeah, basically, so for the quantity that I'm going to talk about, actually, the reason saturation happens is just because of the discreteness of the spectrum. Yeah, for complexity, you need to be a little bit more careful, but the intuition is really just that, energy is conserved under this time evolution. So if the dynamics is, or the state is captured by some finite energy shell, states in a finite energy shell, then it's effectively like a finite dimensional Hilbert space. But I agree, you need to be more careful with.
You have in mind some sort of microcanonical ensemble.
Yeah, so if you were to kind of go over to some microcanonical type ensemble, then this would be a rigorous argument. Yeah, for the thermophile double, you need to be a little bit more careful with the tails.
Thanks so much.
Okay. Okay, so why do we even have a chance of seeing something like this saturation in gravity? So that's what I'm supposed to tell you, but why do we expect that? And it's like a very hard think it seems impossible, but in recent years, we have kind of learned that the Euclidean gravitational path integral, or just like saddles in Euclidean gravity, seem to have like really an unreasonably large regime of validity in describing the microscopics. So there are some examples of these that are now pretty famous, and I just put up here. For instance, you can capture the universal energy level repulsion, random matrix energy level repulsion of chaotic systems, or you can capture the page curve of an evaporating black hole. So the fact that the entropy of the black hole, or the radiation, once the black hole becomes smaller in size than the radiation, it starts to go down. Okay, so how are these things are captured by Euclidean gravity? They are both related to summing over topologies. So for the energy level repulsion, you need to look at wormholes connecting disconnected Euclidean boundaries. And in the case of the page curve, it's basically, in order to calculate an entropy, you use the replica trick, and then again, the different replicas can get connected by gravitational wormholes. Okay, so this is the general kind of message that we've been picking up in the last few years. So emboldened by this, basically today we will ask how do these same effects affect the volume of the interior. Okay. So where we will be able to answer this question is not in a complete generality or a complete argument in any kind of theory, but instead we revert to two dimensions, to JT gravity and its cousins, which are certain dilaton gravity theories where we can answer this question exactly. Okay, so here is JT gravity. As I said, it's a 2D theory of gravity. There's an Einstein-Hilbert term coupled to a dynamical dilaton, which makes this theory non-trivial. And then there's a boundary term, just for a defined variational principle, and like a term for holographic renormalization. Okay, and here, this is the Euler character, and it gives you like a topological term. So this theory is kind of describes the universality class of black holes, you could say, near extremal black holes. So it arises by dimensionally reducing a large class of near extremal black holes in their near horizon region. Not all of them, but a large class. Okay, so there are black hole solutions in this theory, and they are basically very simple. So they don't have a dynamical space-time that is very different from the vacuum. Instead, all solutions are basically global ADS. You can see it's just the equation of motion for this dilaton that sets the curvature to be -2. And the non-trivial dynamics is all pushed to the boundary. And the boundary is basically located at a cutoff surface, as in usually in ADS CFT, and the cutoff surface is gauge invariantly derived by or fixed by fixing a large constant value of the dilaton field. So we're looking for constant surfaces of the dilaton. And for instance, if you look at global ADS2, then a constant dilaton surface will look like this blue curve. So essentially, this really behaves like a two-sided black hole, because this is the boundary, and if you're at the boundary, you effectively see a horizon, and you cannot really send signals between the two boundaries. Moreover, yeah, so you can pick sort of Rindler coordinates in this exterior region that corresponds to this boundary here, and you just have a kind of Schwarzschild coordinates there. So that's the Rindler patch. And then if you go over to Euclidean, again, you have a toy model for the Euclidean black hole, because you just have a hyperbolic disk with a constant cutoff surface. So it's a model for the CERN geometry. Okay, so what happens when you want to include higher topologies? So it's been shown in beautiful work by Saad, Schenker, and Stanford that you can do this basically to all orders in the genus expansion. And you would calculate, for instance, the partition function by first including the disk topology, and then including genus 1 and then genus 2. And then the way that this is done is by surgery. So basically you cut open these surfaces along geodesics, and then you have some contribution from a sort of bordered Riemann surface times a sort of universal piece here. You could call this a trumpet geometry, and you can do these path integrals over the shape of the boundary for both this trumpet and this disk geometry exactly. And basically the upshot of this genus expansion is that this theory is equal to a certain matrix integral. So you have the JT gravity calculation of this partition function, and this expansion here agrees to all orders in the genus expansion with an integral over a random matrix that you may interpret as a Hamiltonian with some potential, and the sort of quantum partition function trace of e to the minus beta h in that theory. Okay, so this squiggly line is just that I swept a lot of details under the rug. So this is true in the genus expansion, and it's true in a kind of double scaling limit of this matrix integral. So these are really infinite dimensional matrices where you zoom to the bottom of the spectrum. Okay. So now let me move on to describe the volume. So let's look at the classical volume in this classical black hole geometry first as a warm-up. So as I told you, this is just ADS2 with a kind of boundary that has this trajectory. So because this is ADS2, it's very easy to find extremal surfaces. They are just vertical lines here. So essentially all this growth is coming from is like how this attaching point falls here to the boundary, or to the conformal boundary. And then if you calculate the length of this, the renormalized length of this geodesic, you find this simple formula. And in particular, as in the case of all black holes that we know, it indeed grows linearly at late times after some transient behavior at early times. Okay, so how do we move away from this classical calculation and talk about a quantum volume? So we will do it in two steps. First, we will not worry about other topologies, just sort of loop effects in the gravity path integral. And a very easy way of doing it is really if you have access to sort of the wave function that you calculate by gravity for the term of your double state, this Hartle-Hawking wave function. Then you can just calculate this as a sort of quantum expectation. You take modulus squared of the wave function depending on this geodesic length. You have some measure with respect to which these are, you know, like an orthonormal basis, and then you insert a copy of this length. And the nice thing about this theory is that, as I was saying, these kind of integrals over the shape of this boundary here. So here we need to do an integral where we integrate over all shapes that have a fixed length here, fixed to be beta over 2. And these integrals can be done exactly. They are one loop exact integrals in this theory, and you get, I just put here this formula so that you can see that there exists like simple formulas for objects like this. Okay, so you know you can put this formula in this other formula here, and you have 3 integrals in total to do. You can either do it numerically or as the way you want. So that's the sort of effect of loops, gravitational loops. There's only one loop effects here on this volume. Okay, so we want to do something more. Yeah, by the way, just I didn't say, but this thing, of course, still grows linearly with time at late times. So the growth coefficient can change and receive loop corrections, but you can confirm that this doesn't affect the fact that it keeps growing. Okay, so now we want to include the effect of topologies. So here there's a challenge that we face that we didn't have on the disk topology, is that if you're at higher genus, then there's an infinite number of extremal geodesics connecting two boundary points. Okay, so here's just a basic illustration of this. So if you look at genus 1 with one boundary, then you can go this way between these 2 points, this way or this way, and actually you can go even more ways. And one way to see this is to cut open this surface. So you can cut open along the red and the blue lines. So then it becomes a piece of the hyperbolic disk with identifications. So you can see that it's a problem of a hyperbolic billiard. So the question is like, what are the trajectories that go from this point to this point? And there's an infinite number of them because you can bounce many times. Okay, so taking the minimal geodesic, so the question is what you do then. So one thing that you could do is like a very classical thinking is to pick the minimal one between these, like the one that actually has smallest length. But this is not very good for our purposes because this is a Euclidean calculation here that I'm describing to you, but in the end I'm interested in how this thing depends on Lorentzian time. And the minimal geodesic in Euclidean, it jumps around if I move this point. It changes abruptly, so this is not an analytic function of the anchoring point, so it's not clear how would you ever continue that to Lorentzian signature. And also it's not a very quantum definition to just like get rid of everything and keep the minimal one. So we want something that sort of has contributions from all these geodesics. Okay, so the most naive thing then to do is to take them on equal footing and average over all of them, basically. So you could imagine having a formula like this. You sum over the surfaces with a given genus, and on a given surface you sum over the geodesics connecting the two endpoints, and then for each of those choices you do the sort of loop integrals, which constitute of integral over the wiggles of the boundary and the moduli space of the internal border Riemann surface. Okay, so there's one obvious problem with this, is that we're summing over longer and longer geodesics, so this expression doesn't make sense. It's a divergent expression, but we don't get scared of divergences. We're physicists, so we go ahead and regulate them. So one way of regulating it, and so I'm describing this regulation, but actually what I'm saying, the end results are independent of how you regulate this sum. So one natural thing that you can imagine is that instead of summing over the length, you sum over e to the minus some delta times the length. So now this is nice and convergent. And then you can recover this formula here by taking the delta derivative and then sending delta to 0. So you remove this regulator. Okay, and one reason why this kind of object is very natural, like this type of regulator, because it's related to a 2-point function. So in general, if you have a heavy particle, then the 2-point function between space-like separated points is approximated by exponential of minus the mass times the geodesic length. And actually that formula in 2 dimensions in ADS2 is exact. So this is something related to the 2-point function. Okay, so how do we calculate this? Basically, the calculation is intuitively very similar to what I was telling you in the case of the disk. So in the case of the disk, we had a bra and a cat wave function, and then we were inserting here something. So in this case, we insert this regulated volume, and then we integrate over all possible values of the volume or the length. So instead of this, what we end up with at higher genus is that we have some higher genus surface, and then we need to cut along some geodesic that ends between 2 points in the boundary, and what that gives us is 2 boundaries instead of 1 boundary. So now you can see this blue is some original asymptotic boundary, and the red is a geodesic. Okay, so this is the type of integral that we need to do. So here we just had this wave function, and in this case we have this sort of contributions here, these psi trumpets that depend on this L or the beta here, and the size of this geodesic here, and then you integrate this against some volume of some moduli space of Riemann surfaces and two geodesic boundaries. Okay, so this is the type of formula that you end up with, and this is like the way to get to this formula is not very trivial, because as you see here, I don't sum over any kind of geodesics, but instead I have a volume of moduli spaces with two boundaries, and that's where a non-trivial magic has been introduced, namely the recursion relation of Mirzakhani, which essentially what it buys you that it turns the sum over geodesics into, and the moduli space with one boundary into something where you don't have the sum anymore, and you have a moduli space with two boundaries. Okay, but intuitively it's a very nice kind of picture that you get here. Okay, so once you do this, then you get a result. So, and the result has the form, because you had these kind of two boundary surfaces appearing. So the result has the form that you can interpret in terms of a matrix integral. So when you kind of collect the terms, you end up with a formula like this. So you have a double integral over energies, some Fourier factors here, and the result depends on this spectral density 2-point function. It's a 2-point function again because you had when you cut it, you had two boundaries. And then there's some kernel here that goes into the calculation, but all the genus expansion is basically sent into this correlation function, so it hides in here. Okay, and the important property of this kernel, so now you can go ahead and try to analyze this expression. And the important property of this kernel at late times is that it has a double pole when the energies coincide. So why is this important at late times? Just to reiterate, because you have this Fourier factor here, and time couples to the energy difference at very late times corresponds to very small energy differences. Okay, so this double pole is the important feature here. Okay, so now what do we expect from this this expression in a random matrix theory? So in a matrix integral, universally, you have a kind of formula for this spectral density 2-point function when the energies are very close to each other. And it's a universal formula, and it's this kind of approximation. So there are several terms here, so let me explain them. The first term is just a kind of disconnected correlation function. So the product of spectral 1-point functions, and geometrically it corresponds to just a product of disks. So it's sort of a classical contribution. Then there's a contact term that you don't see in the genus expansion, and if you were to substitute it in here, it would give you a time-independent divergence. But this is something that is, for instance, regulated by this data regulator that we introduced before. So why is this time independent? It's time independent because it forces the energies to coincide. So even if you regulate it, this part here, this M part, this will not introduce any kind of time dependence. Okay, and the star of the show is this this last term. It's called the sign kernel. It has two pieces. First, it has this denominator here, which is a kind of power law decay. It describes energy repulsion of these random matrix models. So it's a universal feature of chaotic systems. And in terms of the gravitational path integral, it's captured by this kind of double trumpet contribution, which is a wormhole between these two boundaries. And then you have a kind of sign here in the factor that's, or in the denominator, which is a sort of doubly non-perturbative contribution because it goes like the exponential of the 1-point function of spectral density. So it's a bit difficult to understand these in gravity, but we know from random matrix universality that that they are there, and they are required to fix this correlator to be finite when the energies actually coincide. Okay, so now we have this universal result. That's an odd result, and we can just plug it in here and see what we get. So if you evaluate this integral in this way, then you find this. So you find an orange curve like this. Yeah, so that's something you can do numerically, and at early times, which still means long times, you find this classical linear growth. So here we have scaled out this entropy factor both from the volume, or this length here, and the time. So you can do this. It's a scaling formula. So you have this linear growth, and then after a while it saturates. So it has this kind of funny saturation, and it will plateau at a constant. Okay, so this is happy because also from the kind of complexity arguments, we were expecting that we should see some kind of saturation. Okay, and this happens because of a cancellation. So let me talk a bit about this cancellation. And in the same time, compare this finding to more well-studied quantity or description of the spectral 2-point function, which is called the spectral form factor. So the spectral form factor is defined as a product of two partition functions continued to complex temperatures in this way, and then you do an average in the random matrix ensemble. Okay, so this is again something that's sensitive to the spectral 2-point function, and if you calculate it, you get a very similar formula to what I was showing you. Just you don't have this kernel that gives you the double pole. So for this spectral form factor, it's just a 1. Then for the volume, you have this kernel. Okay, so what's the difference that this gives rise to? So both of these test this formula. So this is this universal formula that fixes the behavior in time. So in the case of the spectral form factor, you have a sort of decay. So that's the classical contribution, but then this decay doesn't go on forever, but then it gives way to some ramp here, which is also something that grows linearly, but as I will explain in a minute, it's different than this linear growth. And then this thing also plateaus, but it plateaus at a very small value, exponentially small in the entropy. So this is a log scale here. Okay, so which contribution gives which? This classical disconnected contribution in this case gives the thing that decays forever, while in the case of the volume, it gives the classical contribution, which I was saying is growing forever. So here, this thing is becoming very large, and it needs to be cancelled. And then the sign kernel, this total thing here, for the spectral form factor, it gives this ramp and this saturation. On the other hand, for the volume, it gives something that stays very small until exponentially late times, and then it becomes to decay linearly in exactly the same way as the classical growth. So it cancels this classical growth. So the thing that I want to emphasize is that here, the reason why this ramp, so this ramp in the form factor is coming from non-perturbative corrections, and it ends because of doubly non-perturbative corrections. On the other hand, in the growth of the volume is coming from classical contributions, and it is cancelled by non-perturbative contributions. So it's a different cancellation. Okay. Yeah, I hope that was more or less clear. So now I will move on to the last part, and I have no idea how I'm doing with time. Yeah, sorry. So
you have time. You have about 20 minutes.
Okay, sounds good. Yeah. Okay, so now the last part of the talk about the microscopic interpretation. So this is largely under construction, so take it with a grain of salt, maybe. Okay, so first, the important point I would like to make is that I was showing you a formula that depended on only spectral density 2-point function. So this is a formula that I derived you, or I told you that is derived in a particular theory of gravity that's dual to a particular random matrix theory. But the formula in the end makes sense in any random matrix theory or any matrix integral. So this in itself is not a very impressive statement, but on the other hand, you can study what happens when you deform this JT gravity a bit. So you can turn on some classes of dilaton potentials, and it turns out that you can actually do this and still have a random matrix integral where you deform the potential for the random matrix a little bit. So this has been studied by Maxfield, Turiaci, and Witten. And if you do this, then you just end up with the same formula, the exact same formula, and all the difference between the theories just goes into the spectral 2-point function. So it seems to make sense to just drop the random matrix average and in a fixed quantum mechanical system define a quantity where you, instead of having the spectral integrals and the spectral density, you have a sum over the whole spectrum. So this is the kind of quantity that that you can define that will give rise to the volume after. So this is a little bit simplified. I only keep this double pole here, so the late time physics. But this is the quantity whose average will turn into the volume in the appropriate random matrix ensembles. So let's call this quantity now, defined for a fixed quantum system, spectral complexity, just inspired by holographic complexity proposals. And then the question that we want to answer is that whether we can interpret this quantity. So what is this measuring in a quantum system? Okay, so for this I will step back a little to this idea of complexity and try to just ask what is really complexity supposed to measure, in this case of, like a time evolution. And you could come up with an extremely simple proxy for complexity. Is just to ask how much of the Hilbert space is spanned if you keep all the states along a time evolution. So first you have just a state, so that's one dimension, and then you make a time step, then you have two states, and so on. Of course, these are not orthogonal, but you can ask like how much of the Hilbert space is spanned. So this is the set that we want to look at. Suppose you have all these states. What is it good for? So how do you measure this? So the most naive thing to do would be to sort of kind of integrate the projectors together, like how you would form a projector. If these were orthogonal states, then this is how you would form a projector. And in this case, this is so even though they are not orthogonal, this gives you a density matrix. So if you do this time integral, you kind of time average these states, then you get a density matrix. It depends on some time window t, size of a time window, capital T. So the first guess as a kind of measure of the size of this Hilbert space or subspace would be the rank of this state. But precisely because these time evolved thermofield doubles have for any time some non-zero overlap with each other, this is not a very good guess because this thing is instantly full rank due to extremely small eigenvalues that correspond to states outside of this time window. However, you could kind of refine this and introduce a tolerance, let's call it epsilon, and we replace the rank by some rank, regularize the rank that counts eigenvalues bigger than this tolerance or threshold. Okay, so epsilon is something that we want to choose in a smart way. So we imagine it to be, if we work in, again, in some Energies shell, then it's something that goes like e to the minus s. Okay, so now I just pulled out some quantity from the hat for you, and gave you maybe some motivation of like why it's something similar to what this complexity is supposed to do. But then you can ask, how is it a proxy for complexity? Can I say something more precise? So I will not be able to say something extremely precise, but here's a little bit of a further way of thinking about it. So you could consider a special notion of complexity, which is not complexity of a state, but instead the complexity of an ensemble of states. So let's call it this curly E. So the way we will define complexity of this ensemble of states is the minimum number of gates that you need to prepare the whole ensemble, any state in the ensemble. Okay, so then this kind of quantity, this type of ensemble complexity has, you can kind of lower bound it. It's easier to lower bound it than in the case when you just have one state. So these kind of lower bounds have been introduced by Roberts and Yoshida, and basically they are just in terms of the size of the ensemble. And this is some generic counting argument. So you have a log of the size of the ensemble, and then there's some choices involved, like how many elementary gates you have and so on, and that you can summarize as like a factor of log choices. And then this bound can be very bad, for instance, when there's just one state here, but this bound is getting very good when this ensemble is sort of becoming a linear subspace. Okay, and you can also sort of argue that the left-hand side, at least, this ensemble complexity is roughly the same as the complexity of the most complex state in the set. Okay, so that's a kind of connection point with state complexity. Okay, so now we will consider a special ensemble. So I was telling you about this time average density matrix and how I can, regulate the rank by looking at how many eigenstates are with eigenvalue bigger than some epsilon. So then let's take this ensemble to be this kind of subspace. So subspace with eigenvalues bigger than this threshold. So this is now a subspace. So this bound is working pretty good. And then the volume of this subspace, you can sort of, you can kind of cover it with some balls of some size. You want to measure distinct physically inequivalent states. So essentially you're looking for the volume of some CP projective space to the dimension of this space, and that goes exponentially. It's pi to some power. The dimension of this space is precisely this rank. Okay, so what you find is that this notion of complexity is lower bounded by this regularized rank. Okay, so that's a type of complexity intuition that you can give to this quantity. And one final comment is that so this is now this ensemble quantity, but it's tempting to think that the most complex state in this set of states that you can linearly combine out of thermophile double states up to some time capital T is the TFD itself at time capital T. So there will be other states in this set that have the same complexity, but you don't expect to have more complex states there, maybe. But this is just maybe some hope. And then it's true that if you want to superpose states with different amount of time evolution, that's cheap in a complexity sense. It has some small overhead, but you can do it in a cheap way. So combining these statements, you might hope that that this kind of complexity equals roughly the complexity of this thermophile double state. Okay. So now I told you various different things. So let's kind of, but I try to convince you why this kind of rank of this time average density matrix is important when you regulate it by this epsilon. So how do we calculate this? In a finite dimensional system, we can do this very easily, but in gravity, this is hard. So we want some further simplification, but there's a simple further lower bound on this rank. And you can obtain it by basically Cauchy-Schwarz inequality, writing this type of Cauchy-Schwarz inequality and then minimizing the left-hand side over all possible choices of rho. So it's minimized for a maximally mixed state. And then basically what you find is that this regularized rank is bounded from below by the inverse of the second Renyi entropy, provided that epsilon is sufficiently small. And we may call this, or we will call this effective dimension. So for instance, for a maximally mixed state, this definition of this inverse second Renyi is actually the dimension of the support of the state, but it introduces some kind of regularization that is independent of this choice of epsilon. It works for all reasonable choices of epsilon, and gives a kind of regulated version of this dimension here. Okay, so after this story, this is something that is easier to calculate. So let's try to see how it looks like for this time average state. And what you find is why we made this long kind of a journey here is that it has this kind of form where z is the partition function, and this thing in red here, this c is precisely the spectral complexity that I was advertising. So this is a quantity that is closely related to the volume in two-dimensional gravity. Okay, very good. So one thing to note here is that the typical behavior of this spectral complexity, as we discussed, has this kind of linear growth and plateau. And this effective dimension does the same thing, but since they are not just proportional to each other, but they are actually like there's a non-trivial function here between the two, the slope and the plateau can be very different, even though they scale the same way with the dimension of the Hilbert space or the entropy. Okay, so let me just list the pros or the kind of the good sides of this kind of quantity with a clear, interpretation. So first of all, I argue to you that this is a proxy for complexity, and then, as I show here, it's a direct function of the delay time volume in two-dimensional gravity of the black hole interior. And what I haven't told you about is that it also has nice properties. The effective, it has rigorous Lloyd's-like bounds, so it cannot grow arbitrarily fast, and this is just related to old results about the speed limits on orthogonalization of quantum states. And it's also something that's subadditive for joining evolutions, different pieces of evolutions, and that's something that complexity satisfies as well. But there are also cons, so it's not a perfect find. So first of all, it's not a direct function, like it's not proportional to the volume, it's some function of it, and this causes some weird properties. For instance, the early time slope is different. So it starts as this kind of division here, this t square over this spectral complexity. So when this grows linearly at early times, then this thing also grows linearly, but the growth coefficient is the inverse. And also another important point is that I went to long lengths to show you that the volume saturates at very late times, so the linear growth stops. But the saturation of this effective dimension has nothing to do with the saturation of this complexity here, simply because you have this 1 over t square factor. So this nominator here could grow forever, and this effective dimension would still saturate. So they are not the same physical effect. Okay, so let me tell you some more cons, or more problems with this quantity that we should understand. So I was telling you about only the thermophile double state, but we should also understand the dual of the volume in other states than the thermophile double state in order to claim victory. So one thing that we can look at, a simple thing is to have some operator insertions on top of the term of the double state. And for instance, if you do it at some very early times, it's sort of like a precursor operator. The way you would prepare this state is that you would time evolve backwards for a long time, then insert this operator, and then time evolve forward back to time 0. And both for the complexity and for the classical volume, there's a sort of so-called switchback effect that tells you that the complexity of this state is almost the length of this contour, this total contour, but it's a little bit smaller. Okay, sorry, I don't know what happened. And the reason that it's smaller is that there's a cancellation between the forward and the backward part of the contour. So notice if you didn't have this operator here, then these contours would cancel exactly. But now if you have the operator, it disrupts this cancellation, but there's some time that is needed for the operator to grow large and disrupt this cancellation in a significant way, and that's controlled by a time scale called the Scrambling Time. So I denote it by T star here. In this red region, you have the cancellation, but in the blue region, you don't. So roughly you expect the scaling with the black length of the black regions, which would be 2 times TO minus T star. Okay, so now how would we calculate the effective dimension for a state like this? So we need to average over the time evolution of the states and define a density matrix like this. So what you would need to do is kind of average these states, this time evolved term of your double states, as you go back to the past to minus TO. And then there you would insert this operator at that time, and then you would go forward in time. So you would get some time average density matrix like this. But then you can show that the second Renyi entropy of this only depends on the 2-point function of this operator O. And that's a bad thing because the 2-point function doesn't know about this scrambling time scale. It's just a general fact about operator growth. Okay, so essentially we are not completely sure how to remedy this, but you need to look at some other kind of quantity or some modification of this, maybe that reduces to it in the special cases of the term of the double. And one clue to look for is again gravity, because we can just consider these type of states in gravity and try to obtain a microscopic formula. So this would involve limits of SL2R6J symbols for those who know why this would show up in JT gravity. I send my respects. So stay tuned. This is something under construction. Okay. So let me summarize the talk. So I have told you about a regularized version of a non-perturbative volume in JT gravity or two-dimensional dilaton gravity in general. And then I showed you that it saturates at times exponentially in the entropy of the black hole, and this is in line with what is expected from complexity. So the result that you get is sensitive to the spectral density 2-point function only. So this is very similar to the spectral form factor, but the origin of the ramp and the plateau in the two quantities are different. And then I have shown you that the volume is basically the microscopic formula that you get is a simply calculable quantity and that you can call spectral complexity. And the main questions that I have touched upon that we are trying to answer is that whether the spectral complexity can match some definition of complexity or whether it can give a bound on some definition of complexity. Is the time average density matrix that I kind of came up with in order to mesh this quantity and give it some intuition, is it relevant at all? And what can we say about other states than the term of field double state? And with this, I will stop and thank you for your attention.
Thank you so much, Gabor, for the wonderful talk. Are there questions for Gabor? So I have a question. This time average density matrix that you defined, right? And you talked about D effective as the second Renyi of this density matrix as D effective, right?
Yeah.
You try to motivate this as the overall Hilbert space that all these states at various times span, but I found that connection a little bit, maybe I did not quite understand it properly. You're basically, what you're doing is that you're adding these projections.
Yeah.
Right? But how is that, how does that correspond to, you're averaging, this is like an average, time average projection. How does that correspond to a total? I guess I'm missing maybe a simple intuition as why this is the total Hilbert space that's exploring.
It's not a total Hilbert space. It's like the, yeah, so it's, you're trying to add these thermophile double states, right? And if they were orthogonal projections, and you were always using a new orthogonal state, then at every time step, you would have like a larger Hilbert space that you span by these states.
Sure.
So that's the intuition, and that is what roughly is happening at early times. But then once this density matrix starts to become, you know, like a mixture of many different times at a big time scale, then there will be given linear dependencies, and that's where the saturation is coming from.
The reason I was asking this is that in the old, like 2009, 2008, around that time, literature on equilibration in the quantum information community, this is a setup where you take a system, you look at the subsystem, you put the, you look at a subsystem of it. The global system is in some pure state that belongs to the microcanonical ensemble of fixed energy, and it evolves in time. Then people usually define an effective dimension for the reduced density matrix, and it's defined as a second Renyi of the reduced density matrix of the, well, the average reduced density matrix of the subsystem.
Right.
And well, when I use the quantity that you define looks suspiciously close to that, but I mean, over there is a very natural interpretation. Maybe I can actually try to ask my question a little bit differently. Well, it's not a question, it's more like a, well, it's a collection of thoughts. So for a while now, we've been looking at this time evolution, or if you want to call it half-sided modular evolution, right? That's what it is, right? As maybe a way of coarse graining. So what you are doing, to me, it seems like a natural coarse graining if you were to define some sort of a long distance infrared, or sorry, low energy observables for a system that we do not want to deal with momentum modes. For example, it's like a quantum mechanical system. So this naturally seems to pop up in that setup. But I never thought of it as a measure of complexity.
Right. Yeah, I think it's natural to think about it in a way that you describe as well. But yeah, the fun thing is that it's also sort of like it's some similar toy thing as complexity, because it just like counts how much of the available Hilbert space has been explored by time evolution.
Don't you think that in the same sense that you were discussing at the very beginning, there's nothing unique about this quantity in a sense? It's like there's a whole zoo of infinite number of such quantities you could define that are sort of like behaving like complexity.
Yeah, that's right. But here, yeah, so I didn't emphasize that, but yeah, so when we start to move on to JT gravity and talk about the extremal volume, then we're looking at a precise quantity on the gravity side, right?
Yes.
You can imagine that you want to know what's that in the boundary, and then it will share some properties with complexity, but it has to be a little bit more than that.
Okay, thank you so much. Are there any other questions for Gabor? If not, let's thank Gabor again.
Okay, thank
Great,
you.
thank you so much.
Thanks so much, Gabor. And we're going to post this on YouTube if you don't mind.
Sounds good.
Have a